Today we are going to talk about viscosity values. More precisely, we will talk about the viscosity of the slips, the so-called barbottina, trying to look a little bit closer at the most important reasons of increasements that may seem too rapid and too high. The question is simple. Why and what are the origin of such improper increasement, and what we can do to manage, or even better, to prevent this phenomenon? Let's go and let's see. I am Davide Trentini, and this is Apparently Invisible Chemistry in Ceramics. Good. As we usually do, even today, we start with a definition, or in this case, with a very short identikit of a slip or barbottina. We have already done it in the past, but it's fine if we do it again now, just as a reminder. So, the slip is a viscous matter resulting from mixing water, clays, and other raw materials by means of a wet grinding process. It's a mix, or even better, a suspension that makes the basis of ceramic mixture. Barbottina is a suspension that can be marked by different density values according to the ratio of each component and to the chemicals involved, with particular reference, of course, to dispersants. So, three are basically the main ingredients: inorganic raw materials, water, and dispersants. The rates, or the dosage, of raw materials and chemicals are usually defined and developed to reach, at the end of the grinding process, a slip that is marked by the highest density as possible. This means that the slip must contain the lowest water amount. Why? Even in this case, we already gave an answer to this question, but let's do another quick refresh. The answer is very simple. The reduction of water amount surely increases the industrial productivity, both during the milling process and inside the atomizers. And this reduction, in fact, significantly reduces the energy consumption of the atomizers that must promote a proper evaporation process, turning the barbottina into atomized powder that, under the weight of the press, will form the raw ceramic tile. But what do we mean with reduction of energy consumption? We mean that the water elimination, that is, evaporation and drainage process, is developed by using very strong heat sources. And the higher the water content, the more energy will be used. This is quite clear and obvious. However, we should also add that the frantic search of high density may sometimes compromise the use of the slip itself, because even a very small change in the standard production conditions may lead to a sudden and rapid increase in the slip's density values. But this is not the worst, because in case of a very high values, the problems that arise can also lead sometimes to stop the production line. And now, since we have introduced the word viscosity, let's try to give, even in this case, a very short definition, just to frame the picture. Viscosity, or viscous friction coefficient, measures the attitude of a substance on generating friction between its layers. In other words, it defines the fluid resistance to flow. One more info. In liquids, the viscosity coefficient is normally inversely proportional to temperature. That means that the more the temperature increases, the lower is the viscosity value. And from a microscopic point of view, the value of viscosity depends both on the shape and size of molecules and on their kind of interaction. Well, after this long introduction, let's get right now into the heart of our subject, starting with a question. What are the most important critical issues promoted by a too high viscosity value? We can start by saying that an excessive viscosity, especially when it occurs together with high flow limit and thixotropy values, may promote several and different problems. The most frequent and significant can negatively affect the grinding process, making it more difficult, very more difficult. For example, the discharging times of the slip can be slowed down, and sometimes the process can even remain incomplete. That is not completely discharged on the ceramic support. Sometimes, instead, the criticality may arise during the sieving process that is developed to select the proper grain size of the suspension solid part. In other cases, scale and jelly phenomena can take place inside tanks and pipes, forcing producers to partially or totally stop the process. But before continuing, I would like to underline that these are just a couple of examples to give you an idea, of course, because the list of the problems could be very, very, very long. That said, here is a new question. If all the previous examples are about consequences, what are instead origins and causes that can significantly increase the viscosity value of a slip? Even in this case, we decided to offer here the three most representative scenarios. The first is surely all about the grinding water when it's rich in ions. What does that mean? It means that high amount of ions considerably increase the water electrical conductivity, resulting in turns in higher viscosity values. This is the reason why it is very important to check the water electrical conductivity to avoid problems and to prevent change in the rheological values of the suspension, including viscosity. But let's go a little bit deeper. Grinding waters usually consist of well water and treated wastewater deriving from the glazing line, grinding departments, and other stages of the production process. However, treated wastewaters are usually marked by a very high electrical conductivity that can often affect the stability of the watery system by significantly increase the viscosity once again. And so, what can we do? How can we reduce it? And therefore, how can we act on the electrical conductivity of the grinding water? Well, theoretically, there are some methods, such as osmotic systems, that would lower the conductivity values reaching the proper levels. But the problem is that such treatments are extremely expensive, and therefore they cannot be taken into account in any production process. So, what can we do? Is it possible to act in different ways? Of course, yes. The most efficient and effective solution is in the use during the grinding phase of a proper chemical that develops a sequestering action, reducing the amounts of multivalent cations and at the same time promoting a cationic exchange with monovalent ions, such as sodium, for example. What does that mean? Let's try to explain it very simply. Both cationic exchange and sequestrant actions promoted by some specific categories of chemicals give their contribution on thickening the electrical double layer of the clay micellar, promoting a repulsion effect between them and therefore reducing the viscosity value. In other words, these two mechanisms, cationic exchange and sequestrant action, lead to a repulsive action between micelles so that they can freely flow one on the other, reducing the friction. And this action actually does not reduce the conductivity value, but it promotes a deflocculation process, developing a fluidization action within the system. A second action that could be considered, if we exclude, of course, the use of proper chemicals, is to increase the water content within the system. This action, in fact, decreases the viscosity, but at the same time, pay attention, also affects and decrease the density value of the slip. And this, as we know, is not very welcome or appreciated by producers, since a lower density is synonymous with lower productivity. Good. Let's go ahead addressing the second of the three scenarios that we have chosen. A scenario that appears, for example, in the presence of raw materials marked by high plasticity values or in case of high contents of cation or anions. In these cases, there are many actions that can be taken, even if they are usually not very effective. And this is why I don't offer you a list, but I cut the snake off of the head, saying that even if it's an extreme decision, the replacement of the raw materials is, in this case, the right and best way to face the problem. And now, after this very extreme idea, we finally talk about the third scenario before ending our episode. Sometimes viscosity may increase even after the grinding process. And this usually and often occurs due to a bacterial proliferation within the slip. A bacterial proliferation that usually derives from the process waters involved in the grinding process or from clays that are rich in bacteria. What happens? Microorganisms that feed on organic matter expel ionic substances that, since they intensify the ionic charge of the slip, of course, also increase its viscosity value. And by the way, if you want to deep this topic, I suggest you to listen to the episode number 3 that is all about bacterial degradation of semi-finished products. Well, in any case, in these situations, beside the use of biocides able to stop the proliferation, the only remedy is to add the slip with secondary dispersants able to lower the viscosity of the system. And so, between bacteria and electrical conductivity, even today's episode has come to an end. And here is the mantra that I always offer you. That is that you can listen to all episodes on the main platforms and on our app that you can download for free on Apple Store or Google Play by typing Z&S Ceramco. I also want to underline that on our app you can listen to the podcast, but you can also download completely free the PDF with the text of all episodes accompanied by explanatory drawings that surely can help on better understanding the most difficult topics. That said, I thank you for being with us, and I'll be waiting for you at the next stop of our journey through the ceramic production lines. See you soon.